Hello everyone and welcome to our presentation on the flight computer project. In this project, we've developed a system that integrates three sensors, the MPU6050, BMP280 and GPS module. These sensors work together to collect and process data that is critical for understanding and controlling a flying object. The goal of this system is to track orientation, environmental condition and location of the flight in real time. Our objective with this flight computer was to integrate these sensors into a comprehensive real-time monitoring system. The system tracks by key flight parameters like pitch, roll, yaw, pressure, temperature, altitude, and geographical position. All of this information is vital for ensuring the stability, safety, and accurate navigation of the vehicle during flight. For example, knowing the altitude and pressure can help you maintain a proper flight height, while the orientation data can help adjust the flight's tilt and direction. Why use these specific sensors? During flight, an object experiences a variety of forces and environmental conditions. For instance, the MPU6050 provides a real-time information on the orientation of the vehicle, allowing us to understand its movement and make necessary adjustments. The BMP280 helps monitor the atmosphere around the object, measuring pressure and altitude, which are key factors in determining the flight path and maintaining stability. The GPS module gives the location data, including latitude and longitude, ensuring the flight remains on course.
Now that we have introduced the sensors, let's dive deeper into how each of these sensors work and their specific role in our flight computer system. MPU6050. The MPU6050 sensor is essential for tracking the orientation of a flying object. It combines an accelerometer and gyroscope in one unit. The accelerometer measures acceleration along the three axes X, Y, and Z, allowing us to detect how fast the object is moving in each direction. The gyroscope measures the rate of rotation, which tells us how the object is spinning around its axis. To determine the orientation, we use the pitch, roll, and yaw. Pitch refers to the tilt of the object in the forward and backward direction. Roll measures the side-to-side tilt, like when the plane tilts to the right or the left. Yaw refers to the rotational motion along the vertical axis, which helps us understand how the object is turning left or right while maintaining altitude. The values from the accelerometer and gyroscope are processed to calculate the altitude of the object, which is essential for stabilizing the flight, keeping it on track. These values are especially important in flight control system and stability algorithms. BMP280. The BMP280 sensor is a high precision barometer and thermometer. It measures pressure and temperature, which we can use to calculate altitude. Atmospheric pressure decreases as altitude increases. So by measuring the ambient pressure, we can estimate the altitude. This is crucial for understanding the flight's height above the ground, which can affect its control and stability. By combining pressure reading with the standard atmospheric pressure models, we can estimate the altitude. For instance, an increase in altitude corresponds to decrease in air pressure. GPS. The GPS module Neo 6E gives us latitude and longitude, which is critical for determining the flight's exact position. The GPS sensor receives and calculates the distance to travel. GPS satellites broadcast their location and time, and the GPS receiver calculates the distance to several satellites to determine the object's position on Earth. Together, these coordinates allow us to pinpoint the exact location of the object anywhere on the globe.
So let's move into the project now. So as you can see, this is the Arduino Uno board, and you have the MPU6050, the BMP280, and the Neo 6M GPS module, respectively, connected according to the project's requirements. Now, as you can see, this is pretty clumsy. We'll move into the block diagram for further circuit diagrams. So as you can see, we have this 3.3 volt from the Arduino board straight up connected to the MPU6050, that is VCC, and then BMP280 is connected to the 5 volt, as you can see, 5 volt of the Arduino board. And then as BMP280 and MPU6050 works on I2C protocol, we require a serial data line, that is SDA, and a serial clock pulse line that will be connected to the A4 and A5 respectively, and we use the breadboard to interface MPU6050 and BMP280 together. Now VCC of the GPS Neo 6M will be 5 volt, same as our BMP280, and then the transmit and receive will be connected to 4 and 3 of the Arduino board respectively, and as you know, the grounds also will be connected. Now this is the block diagram which we have managed to make it in the project. So as you can see, everything is connected properly, and this is the wires and block diagram. So let's move into the code. So this is the code that we wrote for Arduino and our project for flight controller. So we have included the libraries of Adafruit sensors and BMP280, GPS module, software serial, and the math module. And then you have the code so far for accelerometer, gyro, and we have also used to smoothen the accelerometer and gyro reading. Then we have the libraries to use for BMP280, and so far we have written the code. Now all this code has been loaded already, so we need not load it in the Arduino, and we'll move on to the serial monitor. As you can see, the readings are pretty instantaneous. Okay, I'll zoom into one of the readings for our perusal. Yeah, so this is currently the MPU6050 readings. So what happens is the accelerometer and the gyro readings are taken, and we have used certain formula to calculate the pitch, roll, yaw of the MPU6050 respectively. And a BMP280 readings will give you the pressure measurement, as you can see, in hectopascals, and the temperature readings. Altitude is also provided by the BMP280 reading. Now GPS readings, hence we are shooting it indoors. We won't be able to show the actual longitude and latitude of the device, and we have displayed a message saying unable to connect the satellite. Now these all things will be pretty useful if you are using a UAV or a drone. So this will be used so that it will be able to auto stabilize itself if it's having, say, wind